Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. Last week we finished off the topic of first order logic and we actually finished off the topic of logic altogether for this course. And this week what we're going to focus on is we're going to focus on set theory, and towards the end of the week we'll start looking at how to apply some logic and set theory to some mathematical proofs, and that will continue on to next week where we'll finish off this topic of mathematical proofs. But for now, as I say, we're going to focus on set theory. And I did outline briefly in my introduction video that set theory in itself is actually a really kind of deep and interesting topic, and we're not going to have time to delve into all the technical details. In fact, many of the technical details of set theory are debated amongst mathematicians today, so it's not even agreed upon a kind of consistent definition of what a set is, because there's kind of many paradoxes that can arise when discussing set theory, and this is because it's really at the kind of foundation of mathematics itself. But for the purposes of this course, the kind of idea of a set that we're going to think of it as is just a collection of objects in which the order those objects appear doesn't matter. And all these kind of paradoxes that can arise on the technical levels of set theory, we're not particularly going to consider, because the things that we're working with, these paradoxes aren't going to arise, right? We're going to work with kind of much simpler objects. So within the context of this course, my definition that I give of a set is going to be a perfectly fine, but not the most technical definition of a set. So I just want to start with kind of an intuitive picture of a set, and I'm just going to take this kind of thing here that's kind of I draw this circle to think of like as a bag, and in this bag I'm going to say that I take some objects. I take a red ball, I take a green ball, and I take a yellow ball. And what I want to do is I want to think about properties of this kind of intuitive idea of a set and see if I can draw them over to actually construct a reasonable definition of a set. Well, the first thing that's kind of key to the definition of a set is this idea that the objects that I define in my set must either be in the set or not in the set. So that is, this yellow ball must either be not in the set or it must be in the set. And that might seem fairly obvious, but it's key to the definition of a set that the only things that I can define as elements of objects within my set have this property. And you might think, well, there are no objects that don't satisfy that property. In fact, there are some that cannot satisfy that property, but as I say, we're not going to delve into them too much within this course. And also, another property that I want to have, that I said before, is the order in which the objects appear in my set shouldn't matter. So if I write my objects in kind of this order here, where I kind of have the red, yellow, and green ball in this order, if I switch them round into this order, that those two sets that I have now should be the same. So the previous set should be the same as this set here. Now, this won't be captured within the definition of a set, but this will be captured later when we start considering this idea of an equality between two sets. So we want to come up with a reasonable notion for what this first set that we had, where the balls were in that arrangement, is equal to this new set where the balls are in this new arrangement. So we want to draw that over to our definition. So doing so, let's look at our formal definition for this course of a set. And we're going to say that a set is simply a well-defined collection of objects which we call elements or members of the set. And we'll go into what we mean by well-defined in just a minute. But we use this notation to say whether or not an element is in the set or not in the set, where we write this kind of x epsilon s to say, oh, that is x is in the set, and we draw a line through the epsilon to say that it is not in the set. So this is just our notation to describe what objects or elements are in the set and not in the set. And I said that we would also say what well-defined means. So well-defined in this setting just captures this idea that the objects that I'm putting into my set must either be in the set or not in the set. So we say that an element is well-defined if that element is either in the set or not in the set. This is the idea that the kind of yellow ball must either be in the set or not in the set, and simultaneously with all the other balls, it must be either in the set or not in the set. And the next thing to do now is to just consider some examples of sets and how would we write them, because sets can come in many different forms. I could have finite sets, I could have infinite sets, and how do I write them? Because in fact, there's many different ways that you might see them in textbooks and throughout the course. So the first and most simple case to consider is, let's consider some sets, some lists of elements that are kind of finite and they're of reasonable length. So what I mean by that is, well, we're going to look at these types of notation, which we call set roster notation. And so let's look at some sets of that form. So here we've got A, which is the set containing the numbers 1, 2, and 3. And this is a set that is finite. It contains 3 elements. And it's of reasonable length. And what I mean by reasonable length is it's reasonable to write out all the elements of that set. So we describe the set here by writing out all the elements of that set. And we describe the elements of that set in this kind of curly brace notation as kind of the things that are inside the set. So anything that's inside those curly braces is inside the set A here. And we use that notation of the kind of epsilon notation to say 1, 2, and 3 are in the set A. Kind of continuing this pattern, we'll take another set here that we'll call C, and this is a set containing the elements London, Paris, and the number 2. So what this set is simply demonstrating is that within sets, the elements themselves don't necessarily have to be related in any way. I could just group together a kind of any collection of objects that I want. There might be no relation between them. So if I start reading the first 2 elements, I think, oh, well, this is a set that's containing some elements, some capital cities in the world, but then the number 2 is there, so it's clearly not about capital cities. But it just points out in set theory that we're just talking about collections of objects. We don't care about relations between those objects at this point. In fact, most of the things we're going to be working over and most sets we work with, all the objects are related or all the elements are related in some ways, but there's no reason at the level of set theory that those objects necessarily or elements need to be related. And also, just like before, we can write this notation that London, Paris, and 2 is in the set C. And the final example I want to consider is a bit of a strange one, which here we've got D is the set containing 0, and it also contains the set containing 0. So here we've got 2 elements, so we write these elements here as 0, and the set containing 0 is in D. And notice here that these are 2 distinct elements. So that is the number 0 is different from the set containing 0. So how can we think of this? Well, if you like to think of it as like kind of what I said at the beginning, where that kind of, I had some coloured balls within a bag, that I can think of the curly braces here as like a bag. So this is a bag containing the number 0 and also containing a bag containing the number 0. So clearly the number 0 here is not the same as the bag containing the number 0. So that's kind of how to think of it in that sense. There's kind of 2 different elements within this set. So that is, I can take sets that also contain sets as well, and those are themselves sets. In fact, I don't think we'll go into this too much in the course, but this is how you can actually start defining the natural number systems as kind of sets containing sets. But we won't go into that here. So as I said, this is just considering the kind of simplest case of sets. That is sets that are finite in length and contain a reasonable number of elements. And that way we can we can describe the set by writing out all the individual elements of the set. But that's not generally reasonable, because I could have many sets that are either kind of infinite in size, or I could take a set that is finite, but let's say has like 1,000,000 or 1,000 objects, 1,000 elements. And I'm not going to write out all the elements to describe that set. So is there another way that we can describe sets, or we can describe those types of sets? And we can, and this is known as what we call this set builder notation. So this ties in with the idea of a predicate, and we'll see that in just a minute. So here now we've got B is the set of positive integers, and how we will write that, again we use these curly braces. So we write it as X with a colon after it first, and we read this colon as the word such that. So we're saying let's take all the elements X, such that, and we want to take X satisfying some conditions. In other words, this thing on the right here we're thinking is a predicate, and it's a predicate that's a function of X. So we want to make sure that it satisfies these conditions. And the conditions we want here are that X is an integer, and we also want X to be greater than 0 because it's positive. So whenever we write these things in this set builder notation, we start with our element at the beginning, we put the colon in that means such that, and then we put the conditions that we want on X in order for it to be an element of that set. But additionally, we can also write it in this other way, where we could say, let's take B to be 1, 2, 3, and then write this ... notation. And this ... notation is effectively just saying that we continue the list on indefinitely according to the previous pattern. So we can, importantly, is, to say here, we can only use this ... notation if the numbers before follow a very specific pattern, a kind of very obvious pattern. In this case, we can see that the pattern is that I take the previous number, and to get the next number, I just add 1 to that previous number. So after 3, we would get 4, and after 4, we would get 5, and so on. And because there's no number at the end here, we've just got ... and it's there's nothing at the end. That means we're going on forever. So in other words, this is infinite in length, this list. So this is 2 ways in which we can describe this same set, which is the set of positive integers. And kind of continuing the pattern again, we'll look at another set here that can also be written in the same 2 ways, but this is now going to be a finite set, and it's going to be a finite set that we say is what? It is the set of integers between 1 and 1000, including 1 and 1000. And we can write that again in this set builder notation, that we take the set elements x, set of elements x, such that, so we write our colon, x is an integer, and x is between 1 and 1000. So again, we're thinking of this thing on the right as like our predicate that is defining the property of x in order for it to be an element of that set. And we can also write it using the ... notation, but notice now our set is not infinite, so it doesn't go on forever, right? It ends at 1000. So using the ... notation, what we have to do is we have to write 1, 2, 3, ... and then we end at 1000. So we have to put that kind of last number in at the end to say that's where we're ending, that it doesn't go on forever and ever. So there's also some more examples of different sets that you can write in the notes, and I suggest that you look at them yourselves. But in general, the set builder notation is in fact probably the most robust notation that is used in mathematics, and you'll see that sets are written in many different ways, and you'll get very used to kind of how they're written by just reading a lot of literature around it. But in general, this kind of encompasses most of the ways that we can write sets. So this is where I will finish that video. And in the next video, what we're going to do is it'll be a short video that will start introducing the number systems that you've probably already seen before, like the natural numbers, the integers, the rationals, and the reals. We'll also introduce this idea of the empty set, which is a special type of set. And we'll also introduce this notation, which is describing some ideas of subsets of the real numbers, some special notation. So again, like always, I remind you to look at the notes on the Moodle page and to attempt any problems related to this video within the module handbook. So thanks very much, and see you in the next video.